Hello, welcome back to Scalable Machine Learning. This is our 5th week and also my last week teaching this module. Let me share the screen with you. And this week, we are going to study Scalable Machine Learning for Dimensionality Reduction. We will start with a recap of PCA and discuss the scalability problem, and then we move on to an alternative solution to PCA using singular value decomposition. And next, we will study scalable PCA in Spark. And finally, I will talk about software development life cycle. Let me start with a recap of PCA and also discuss the scalable problem in PCA. We have learned dimensionality reduction in the ML AI module, and we know that the primary motivation for dimensionality reduction is in our real-world data, our raw data. They are complex and high dimensional. And the key assumption in dimensionality reduction is these complex and high dimensional data, actually they lie on a low dimensional subspace. So the access in this subspace will provide a new representation of the data. And we can provide simpler, more compact, and interesting patterns reviewed from the data. For example, this is a dimension reduction from 2 to 1. And that is from 2D space to a single line. And this is a dimension reduction from 3 to 2, from a 3D space to a plane in 2D. And dimensionality reduction is very useful. And we can use dimensionality reduction to discover hidden correlations in data or hidden topics in documents, in text, and also hidden factors. And they can also be used to remove redundant or noisy features in the data. And thirdly, they are very useful for interpretation of our data and also visualization to gain some insights. And finally, they can provide easier storage and processing of the data due to the lower dimension that has been learned. We have learned that PCA is a classical method for dimensionality reduction. It works by maximize the variance captured in the transformed subspace. And the input to PCA are unlabeled data. For example, we have n data points, and each of them are d-dimensional. Then the PCA algorithm works by firstly form a data matrix of dimension n times d. And each data point will become a row vector in this matrix. And then we compute the mean from these rows and then subtract this mean from each row vector. This is called centering. And then we compute the Riemann matrix, also called scatter matrix, for X, for the data matrix, for the centered data matrix X. That is X transpose times X, and we call it sigma. And then we find the eigenvectors and the eigenvalues of sigma. And we keep the top R eigenvectors as the principal components or PCs. And this will give us a projection matrix of dimension D times R. And we can use this learned projection matrix to project a new data point Y, for example, to learn the PCA features by doing a simple linear transformation, which will reduce the dimension of Y from D to R. And on the training data set, these features will have zero correlations, and they will also be ordered by the variance captured. And the scatter matrix is very important for PCA because this is where we compute the PCs from. And suppose we have an image of size 100 by 100, then the D will be 10 to the power 4. And if we have an image of 1000 by 1000, then D will equal to 10 to the power 6. And in these two cases, the scatter matrix will be much larger because the scatter matrix is of size D squared. So if D equal to 10 to the power 4, then the scatter matrix will have a size of 10 to the power 8. And if D equal to 10 to the power 6, then the scatter matrix will have a size of 10 to the power 12. So this will become difficult for high dimensional data. And therefore, we will examine an alternative solution to PCA based on singular value decomposition. And this is because there are very efficient algorithms available for singular value decomposition, or SVD. And we often just need the top R eigenvectors, so we don't need to do a full decomposition, which can also lead to some more efficient computing. So in the next section, we will look at how to do PCA using SVD.